In this video, I am going to solve the second problem based on the design of knuckle joint. This problem was asked in December 2018 examination, university examination. Now let us go through the problem statement. Two rods are connected by means of knuckle joint. The axial force acting on the rods is 30 kilonewton. The rods and the pins are made up of plain carbon steel. The material of both rod and pin is same, plain carbon steel, and its grade is 45C8, and the property, that is yield strength, is given. It is 380 Newton per mm square. Then the factor of safety is given. So this FOS is given. It is 2, and we have to calculate the complete knuckle joint. Here it is mentioned that design the complete knuckle joint. That means we have to solve all the 7 steps which are given in the design procedure of knuckle joint. So first of all, just interpret the given data. So here the force acting on the knuckle joint, that is P, is given. Then the rod and pin are made up of plain carbon steel. That means the material of rod and pin is same. So it indicates that the permissible stresses for rod and pin we have to take same. Okay, so whatever the permissible stresses we are going to calculate for rod, same can be used for pin, and that permissible stresses can be calculated with the help of this SYT and FS. So this is the problem statement. Now let us first of all write down the given data. So let us write the given data. So the force acting on the rod is given 30 kilonewtons. That means P is given. So P is equal to 30 kilonewton. So let us convert it into Newton. So 30 into 10 raised to 3 Newton. So this is the value of force P in Newton. Now next, for rod and pin, the value of property of plain carbon steel is given. That is SYT, yield strength, is given, and it is same for both rod and pin. So SYT is 380 Newton per mm square, and Fs, which is required to find out the permissible stresses, is given. Factor of safety is 2. So this is Fs, factor of safety, Fs 2, and we have to calculate the complete knuckle joint. So complete knuckle joint indicates that we have to solve all the 7 steps. So first of all, now calculate the permissible stresses with the help of this SYT and Fs for both rod and pin. Now we have to write the heading, calculate the permissible stresses for rod and pin. Remember here, whatever the material of rod is there, the same material is there for fork and eye. So indirectly, while calculating the permissible stresses for rod, we are calculating the permissible stresses for eye and fork also. Okay, so because the material of rod, eye and fork is same, so same permissible stresses we can use for eye and fork. Now the first permissible stress that we have to calculate is permissible tensile stress, which is denoted by sigma T, and its formula is sigma T is equal to SYT upon Fs. Now if you refer this given data, the value of SYT is 380 and the value of Fs is 2. So let us put this value. SYT is 380 Newton per mm square and Fs is 2. Now if we calculate this, we'll get the answer as 190 Newton per mm square. Okay, so this is the value of permissible tensile stress. Now second is permissible shear stress, that is denoted by tau. So tau can be calculated by the formula tau is equal to SSY upon Fs, where this SSY is nothing but the yield strength in shear, and this SSY we know that it is in terms of SYT is 0.5 SYT according to maximum shear stress theory upon Fs. Now let us put the value of SYT again. So value of SYT is 380 and Fs is 2. So let us put these values. And the answer of this permissible shear stress tau is 95 Newton per mm square. Okay, so now the third is permissible compressive stress, sigma C. Now remember that the permissible compressive stress, sigma C, can be calculated using the formula SYC upon Fs. Okay, and as I explained in the introduction of this permissible stresses, that if the SYC value is not given, we can assume is equal to SYT. Okay, so we have to write here, take SYC is equal to SYT, and value of SYT is 380. So we can put here value of SYC as 380 upon 2. So we can get the value of this permissible compressive stress as 190 Newton per mm square. Okay, so this is the important point. While calculating the compressive stresses, permissible compressive stress sigma c, the SYC is required, and if the SYC is not given in the problem, then we can take SYC is equal to SYT for this particular case of knuckle joint, and hence we can get the value of this sigma c, that is permissible compressive stress, as 190 Newton per mm square, which is same as that of permissible tensile stress. Now fourth permissible stress is permissible bending stress that we require to solve this problem, which is denoted by sigma b. So now we know that this permissible bending stress, we have to assume this permissible bending stress sigma b is equal to permissible tensile stress, and the value of permissible tensile stress is 190 Newton per mm square. So we have to write this value as here 190 Newton per mm square. So this is the permissible bending stress that is equal to permissible tensile stress, and its value is 190 Newton per mm square. Okay, so we have calculated the four permissible stresses: permissible tensile stress, permissible shear stress, permissible compressive stress, by taking SYC is equal to SYT, and last is the permissible bending stress. So these four permissible stresses are required to solve the problems based on knuckle joint. Okay, now let us start the solving the steps of design of knuckle joint. So now after calculating permissible stresses, now let us start the design of knuckle joint. So first step is calculate the diameter of rod capital D, and we know that from the design procedure, the equation to calculate diameter of each rod is given by capital D is equal to under root 4p upon pi into sigma t, where this p is nothing but the external applied force and sigma t is nothing but the permissible tensile stress. Now let us put this value of p and sigma t here. So I have put here the value of P 30 into 10 raised to 3, which is given in the problem. Then I have put the value of sigma T, that is permissible tensile stress, which is 190 Newton per mm square. And if you calculate, the answer will be 14.17 mm. Okay, and we know that from the manufacturing consideration, we have to round up this value. So generally we add 2 to 3 mm. So let us write the answer of this capital D as 16 mm. So this is the answer of diameter of rod. Now the second step is calculate the enlarged diameter of rod, that is denoted by capital D1. From the design procedure, we can write the formula of this capital D1 as 1.1 times of capital D. Now capital D we have taken as 16 mm. So let us put the value of capital D here, 16. So answer of this capital D1 will be 17.6 mm. Okay, so we have to again this round off the answer from manufacturing consideration. So let us take this value as 18 mm. So this is the value of enlarged diameter of rod. Now the third step is calculate A and B, where A is the thickness of fork end and B is the thickness of eye end. From the design procedure, we can write the formula of A as A is equal to 0.75 times of capital D and B is equal to 1.25 times of capital D, where D is the diameter of rod that we have calculated in the step number 1. So let us put the value of capital D, which we have got it from the step number 1, as a 16 mm. So 0.75 into 16. Similarly, put here value of capital D was 1.25 into 16, and let us calculate this A and B. So answer of A will be 12 mm and answer of B will be 16 mm. So this is the answer of A and B, that is thickness of fork end and thickness of eye end. Now the fourth step is calculate the diameter of pin small d, and the small d can be calculated based on shear stress and based on bending stress. So let us calculate the diameter of pin based on shear stress. Now, in order to calculate the diameter of pin based on shear stress, we know the equation D is equal to square root of 2p upon pi into tau. So this is the equation that we can refer from the design procedure of knuckle joint. Now let us put the value of p and tau here. So I have put here the value of p as 30 into 10 raised to 3 and value of tau as 95. So the answer of this D based on shear stress is 14.17 mm. Now here we don't have to round up this value because again we have to calculate the diameter of pin based on bending stress, and then we will select the maximum one and then we will round up the value of D. Now let us calculate the diameter of pin based on bending stress. So refer the design procedure and write down this equation to calculate the diameter of pin based on this bending stress. So cube root 16p into bracket a upon 3 plus b upon 4 upon pi into sigma b. So let us put the values of p, a, b and sigma b. Now in this formula I have put the value of p as 30 into 10 raised to 3, value of a as 12 and value of b as 16, and in the denominator I have put the value of permissible bending stress sigma b as 190 Newton per mm square. Okay, if we calculate this value of D, so the answer is 18.59 mm. So this is the diameter of pin based on bending stress. Okay, now what we have to do, we have to select the maximum value from these two values, that is the diameter of pin based on shear stress and diameter of pin based on bending stress. So we have to write one statement here. Therefore write selecting the maximum value from above. Therefore the diameter of pin maximum from these two values is 18.59 mm. So therefore let us round up this value. So D is equal to 20 mm. You can add 2 to 3 mm into this final answer of D and you can round up this answer. Now the step number 5 is calculate DO and D1. So from the design procedure we can write the formula for DO. So DO is equal to twice small d and D1 is equal to 1.5 times of small d. So where this d is the diameter of pin that we have calculated in the step number 4, and the diameter of pin we have got as 20 mm. So let us put the value of this small d and let us calculate the value of DO and D1. So the answer of DO is 40 mm and answer of D1 is 30 mm, where this DO is the outer diameter of fork and eye and D1 is the diameter of pin head. So with this step we have completed the step number 5, that is calculate DO and D1. Now the step number 6 is check the stresses in eye. So here we have to check 3 stresses in eye. First is tensile stress, second is shear stress and third one is crushing stress. So now let us check one by one. So first stress is tensile stress, which is denoted by sigma t, which is given by sigma t is equal to p upon b into d0 minus d. So let us put the value of p here. So p is 30 into 10 raised to 3 upon b is 16 into do is 40 and small d, that is diameter of pin, is 20. And let us calculate this induced tensile stress in this eye. So answer for this induced tensile stress is 93.75 Newton per mm square, which is less than sigma t permissible, that is which is less than permissible tensile stress, and the permissible tensile stress value is 190 Newton per mm square. So this induced tensile stress sigma t is less than permissible tensile stress, that is 190 Newton per mm square. Therefore, we can say that design of eye under tensile stress is safe. Now let us check the shear stress tau in the eye. So equation of tau, that is induced shear stress in the eye, is P upon B into dO minus D. Let us put the value of P. B is 16 and dO is 40 and D is 20. Now the answer of this induced shear stress is 93.75 Newton per mm square. We have to compare this value of induced shear stress with the permissible shear stress. If you compare, the value of permissible shear stress is 95 Newton per mm square and this induced shear stress is less than permissible shear stress. So therefore we can write less than tau permissible and therefore design is safe. Now check the crushing stress in the eye, and this crushing stress in the eye is given by equation P upon B into D, where this P is 30 into 10 raised to 3, B is 16 and small d diameter of pin is 20. So if you calculate this, you will get the answer as again 93.75 Newton per mm square, and we have to compare this induced compressive stress with the permissible compressive stress, and the permissible compressive stress is 190 Newton per mm square, and thus we can say that this induced crushing stress 93.75 is less than permissible compressive stress and therefore design is safe. Now in the last step, that is 7th step, we have to check the stresses in fork, and we have to check tensile stress in the fork, shear stress and crushing stress in the fork. So let us check one by one. Now the equation of tensile stress in the fork is given by P upon sigma T is equal to P upon twice A into dO minus D. So now let us put the value of P here. P is 30 into 10 raised to 3 Newton, then A is 12 and dO is 40 and small d is 20. Now let us calculate this induced tensile stress in the fork. So the answer of this induced tensile stress in the fork is 62.5 Newton per mm square. If you compare this induced tensile stress with the permissible tensile stress for this knuckle joint is 190 Newton per mm square. So we can say that this induced tensile stress is less than sigma T permissible, and therefore the design of fork under tensile stress is safe. Now the second stress in the fork is shear stress tau. So we have to find out the induced shear stress in the fork. So its equation is P upon twice A into dO minus D. So the RHS of this sigma T and tau is same, so we will get the same answer, but we have to put here the value of P A dO and D. So we will get the answer same because the RHS of sigma T and tau is same. Now this is the induced shear stress. Now we have to compare the value of induced shear stress with the permissible shear stress for knuckle joint, and the permissible shear stress is 95 Newton per mm square. So we can say that this induced shear stress 62.5 is less than tau permissible, that is 95 Newton per mm square, and therefore design of fork under shear stress is safe. Now the last stress in this fork is crushing stress, that is sigma C. Now the induced crushing stress is given by equation P upon twice A into D. Now let us find out this value of induced crushing stress. So put the value of P, put the value of A. The value of A is 12 and value of D is 20. So if you calculate this, the answer of this induced crushing stress will be 62.5 Newton per mm square. Now we have to check the safety of this induced crushing stress. So we have to compare this value with the permissible compressive stress, and the value of permissible compressive stress is 190 Newton per mm square, and thus we can say that the induced crushing stress 62.5 is less than permissible compressive stress, which is 190 Newton per mm square, and therefore the design of this fork is safe. So we can write at the end as induced stresses for fork are less than permissible stresses. Therefore, design of fork is safe. You can write the same statement for this I as well. So you can write here, as the induced stresses are less than the permissible stresses, therefore a design of I is safe. You can write it here for I as well.